The purpose of this video is to demonstrate the proper use of the Boeing Ramp Damage Checker, or RDC. While the RDC was invented by Boeing, it's marketed by other companies, so your equipment may look slightly different than the prototype we're using here today. The Bond Tracer, manufactured by GE, is one of the commercial versions of the Ramp Damage Checker. The 35 RDC, manufactured by Olympus, is another commercial version of the RDC. Though they look slightly different, these commercial versions of the RDC function in the same way. We will describe them in more detail later in this video. The RDC should not be used to search for damage. The correct use of the RDC is to determine if an area with visible damage, like a dent or scuff, also has subsurface damage. When used properly, the RDC will detect delaminations in composite materials. Because the RDC is a simplified piece of equipment, it is possible to get incorrect data. You must have the proper training to use the RDC. The RDC compares the ultrasonic signal of the current probe location to the signal at calibration. Because the result depends not only on the defect area, but on the calibration area as well, it is critical that the user understands how the RDC makes its decision. First, a little background on the RDC and how it functions. The complete unit consists of the RDC, the ultrasonic probe, and a cable that attaches the two together. To calibrate the RDC, place the ultrasonic probe at least 6 inches or 150 millimeters from any visible damage and push the calibrate button. At calibration, the RDC memorizes the amount of time that the ultrasonic pulse takes to leave the probe, reflect off the back wall, and return to the probe. The indicator light will change from green to red if the unit detects an ultrasonic signal earlier in time than the signal at calibration. The following reasons will cause the red light to illuminate. The RDC detects a delamination. Material thickness decreases by more than 1 ply. There is insufficient couplant between the probe tip and the part. The commercial versions of the RDC function like the Boeing prototype we have shown here, but there are some differences you should be aware of. First, the defect indicators are different. The GE Bond Tracer displays green and red lights corresponding to good and bad areas. The Olympus 35 RDC displays the words good or bad instead of a green or red light. Second, the instruments have different responses to thicker structure. We'll talk more about that later. Third, the Bond Tracer and the 35 RDC have differing displays for power, calibration, and battery life. There are other differences in the way these commercial versions operate. To understand the differences, it is best to read the instrument operating manual. Now that you have a basic understanding of how the RDC works, we'll go through the 6 steps in an example inspection. Visual evidence of damage causes an inspection to be initiated and is step 1. The second step in using the RDC is to determine if the damage is located in a compatible area. The RDC can be used on the blue areas shown in this image. These are solid laminate areas that are less than 5/8 of an inch or 15 millimeters thick. If the visual indication is located in a red area, contact an NDT specialist. Third, draw guidelines on the surface of the structure so that you are able to scan parallel with the thickness changes. The fourth step is to apply couplant to the inspection area. Since ultrasonic waves will not travel through air, it is necessary to use couplant to permit the sound waves to enter the part. Step 5 is to identify a good location to calibrate. The calibration site should be at least 6 inches or 150 millimeters from the visual damage. You must also consider the direction of your scan. Move in the longitudinal direction on the fuselage and an inboard-outboard direction on wing or empennage surfaces. Use a straight edge or ruler to keep the scan parallel to your guidelines. Step 6. Conduct the inspection. When the red light illuminates, the probe has moved to a suspect area. Suspect areas are possible delamination areas and must be investigated further. If the red light doesn't illuminate, recalibrate at the end of the scan and then scan back to the original starting point. When you have identified a suspect area, mark under the center of the transducer with an approved marker. Continue to map the outline in parallel paths until the RDC passes the visible damage without the red light turning on. Make sure that you calibrate and scan into the damage area from both directions. Let's review the 6 steps. 1. Visible damage initiates an inspection. 2. Check if damage is in RDC-compatible area. 3. Draw guidelines parallel to primary structure. 4. Apply couplant to the part. 5. Calibrate. And 6. Inspect. Because the RDC does not distinguish between delaminations and thickness changes, the user must understand how the RDC thinks to complete the inspection accurately. If the user calibrates the RDC in a thick area and then moves to a thinner area, the bad light will illuminate. This is because the signal takes less time to return to the probe, and the RDC interprets the early reflection as a defect. If the user calibrates the RDC in a thin area and then moves to a thicker area, the RDC will not identify defects that occur beyond the calibration thickness, because it only monitors signals that return earlier in time than the calibration signal. This is why it is imperative that the user know where these thickness changes occur. Let's go over this again, using the displays from the bond tracer and the 35 RDC. When scanning to a thinner structure, the bond tracer display changes to a red light, and the 35 RDC display changes to the word bad. When scanning onto thicker structure, the bond tracer display remains green, even if a delamination is present beyond the calibration thickness. The 35 RDC display changes to the words beyond calibration thickness. This means you should recalibrate to ensure detection of delaminations beyond the original calibration thickness. With either the bond tracer or the 35 RDC, the correct procedure is to scan toward the damage from 2 opposing directions. This will ensure that delaminations beyond the calibration thickness are not overlooked due to structural thickness changes. An easy way to find thickness changes on the fuselage is to recognize fastener patterns. Fasteners generally signify a thicker skin area where substructure is attached. For example, shear ties are attached with a row of 6 fasteners. The first and last fasteners attaching the shear ties are always centered on the subsurface stiffeners. These stiffeners are about 1 inch or 25 millimeters wide. The important thing to remember is that the RDC is a simplified piece of equipment. The RDC will give you the correct result as long as each inspection pass is completed on material of the same thickness. It's your job to properly identify those areas. Call an NDT specialist with more advanced equipment if you are unsure of your results.
Boeing.